Okay, in this video, we're going to continue going through the calculus review guide and looking at the integration problems. So here we have a graph of the function y equals f of t, and we are defining g of x to be the integral from 0 to x of f of t dt. And the first problem asks to calculate what g of 2 is. So to calculate g of 2, well, I guess we can do this directly on the review guide. So g of 2, how can we approach this? Well, g of 2 is just going to be, you know what, let me do it on here. So then g of 2 is just the integral from 0 to 2 of f of t dt. And so what that's saying is it's going to be area under the curve from 0 to 2. And so it's this area right here. Notice that's just a triangle. It's a triangle with base 2 and height 2. So its area is 1/2 of 2 times 2, or 2. So g of 2 just comes out to be 2. Similarly, it asks us to calculate what g of 4 is. So to figure out what g of 4 is, we can say, well, g of 4 is just going to be the area from 0 to 4 of f of t dt. And so that's going to be, you're now adding this additional block of area, you're adding the area from 2 to 4. So we already found that this area here was 2, and now we're adding this other block, which is a 2 by 2 rectangle, so that is area 4. And so now we have area 2 plus 4, which is 6. So the area of g of 4 is 6. Similarly, we are now asked to find the area of g of 5. So we say, okay, the area of g of 5 is just, g of 5 is just equal to the integral from 0 to 5 of f of t, which is the area from 0 to 5. So now we're adding in this little block here, this little triangle. Notice this is a 1 by 2, so that rectangle of area 2, the triangle is half of that, so it's area 1. So we've added 1 to the previous 6, so now we have area 7. Area 7. So this guy here is 7. And the last one is, how about g of 6? And so g of 6, same approach, g of 6 is just the area from 0 to 6 of f of t dt. And so that's going to come out to be, well, let's think. We're now adding this little section. And notice this is now a triangle. It's a 1 by 1. So that is area 1/2 of that is 1/2. So this is a triangle of area 1/2. But because it's under the x-axis, it's negative area. And so the total area from 0 to 6 is this positive area, which came out to be 7, minus this negative area, minus the negative 1/2. So that gives us 6.5. G of 6 is 6.5. We're then asked, okay, where was g of x increasing? Well, notice as long as we were adding more positive area, the total area was getting bigger. So beginning at 0, all the way up until 5. But then, beginning at 5, we started adding negative area. So up until 6. We don't know what happens after that, you know. Does the function go on? Is that at the end of it? I'll just say we know what happens up until 6. Then we're asked, where on this interval from 0 to 6 do we have a maximum? Well, notice what we said what happened. You have g of x, and from, well, let's think of it this way. From, you have some interval, and we have that up until 5, it was increasing. And then after 5, it was decreasing. So the maximum would be at 5. The maximum is when x equals 5, which is obvious. You get the most area if you add up all the way to 5. If you add up before 5, you'd miss out someone's positive area. If you go after 5, you're adding negative area. So adding up all the way to 5 is when you get the largest area. Okay. We're then asked to calculate a few derivatives. G prime of 1, G prime of 2, G prime of 5. It's like, okay, a derivative of the integral. This is the fundamental theorem of calculus kicking in right now. Because remember, G prime of x, what is that going to be? That's just the derivative of the integral from 0 to x of f of t dt. So, by the fundamental theorem of calculus, this just comes out to be f of x, which tells me that g prime of 1 is just equal to, so g prime of 1 is just equal to f of 1. Whatever my function is at 1. If you go up here, at 1, my function is 1. So g prime of 1 is 1. And g prime of 2 is whatever f of 2 is. And so you go up and you have, at 2, I'm up here and I have 2. So it's 2. And g prime of 5 is whatever my f of 5 is. And so I go and I look and it's 0. So this is 0. And that makes a whole lot of sense that you have g prime of 5 as 0, because we said we have a maximum. We have a maximum at x equals 5. So derivative there must be 0. Okay. Very good. The next question asks us to think about Riemann sum. And so I'm just going to rewrite it a little bit larger here. It says take this integral, the integral from 1 to 3 of x squared plus 1 dx, and express that as a Riemann sum. So we want to write this as some limit of some sum of... Okay, so maybe you kind of forget the details. And so let's remember the story really fast of how we come up with what this is. So the picture you should have in your mind is you have some graph. Looks, something like this. You have some graph, and you're trying to find the area from 1 over to 3. Trying to find that area. And so the way we find that area is we break this up into a bunch of little rectangles. We break it up into a bunch of rectangles, and then we just add up the area of these rectangles. Now that doesn't give you the exact area, there's some overlap, but as you make more and more rectangles, so we're going to pick n rectangles, and as n gets bigger and bigger, as you take the limit, as n goes off to infinity, you take the limit, this gives you a better and better approximation of the area under it. And so we ask, okay, what are the, how do we describe these rectangles? Well, if you have n rectangles, then we can first think about what the width of each rectangle is going to be. So our width of each rectangle is the total width, 3 minus 1, divided by n. So each width is of 2 over n. So that gives us the width of each rectangle is 2 over n. And then how about the height of the rectangles? Well, notice the height's determined by this right endpoint. The right endpoint tells you f of that is the height. Here You plug it into f, you get the height. Here you plug into f, you get the height. So what are these x values? Well, this first one is we started off at 1, but then you went over 1 width. So you go over 1 width, 1 copy of 2 over n. The next one is you started off at 1, but now you've moved over 2 widths. So 2 times 2 over n. And the next one is you're at 1, but then you move over 1, 2, 3 widths. 3 times 2 over n. And so forth. It continues this way until you get to the last rectangle where you had 1, so we continued for a while. The last one is 1 plus n rectangles we moved over to get to the last one. N times 2 over n. Oh, and notice that happens to come out to be n divided by n cancel, so it's 1 plus 2, which is 3, which is exactly what we expect. We got to all the way to the right. So those are my x values, and then that tells me that the value of the height right here, this height is going to be at f of that x value. So the first one is f of 1 plus 2 copies, 1 plus 1 copy of the width. The next one is f of 1 plus 2 copies of the width. The next one is f of 1 plus 3 copies of the width, etc. So now if I want to find the total area of my rectangles, I go, okay, the area is just going to equal, well, it's the width, 2 over n, times my first one, f of 1 plus 2 over n, plus my width, 2 over n, times the area, the height of my second rectangle, which is 1 plus 2 copies of 2 over n, and then plus the width times the height of the next rectangle, which is 1 plus 3 times 2 over n, plus etc. You end up with the last one, the width times the height of 1 plus n times 2 over n, where this just comes out to be 3. Okay, so you can simplify this by factoring out the 2 over n. So you can pull out that width, 2 over n, and you're left with the sum of f of beginning at 1, adding copies of the width, adding copies of 2 over n. So first you add k equals 1 copy, and then you add k equals 2, and k equals 3, and k equals 4, all the way up to k equals n copies. So adding n copies of up to n copies of the width. So there's our expression for the Riemann sum, which in particular for this function is x squared plus 1. So let's put that in for our function. It's the limit as n goes to infinity of 2 over n times the sum of our function now is x squared plus 1. So here's our x values, 1 plus k times 2 over n squared plus 1, where k is going from 1 to n. Okay, there's our expression, there's our Riemann sum. Now, what we want to do is we would really like to solve this Riemann sum. And that's exactly what the next question asks us to do. It says, calculate what this Riemann sum comes out to be. Now, when you're looking at that, you may be thinking, I have no idea what that Riemann sum comes out to be. Like, that's the right reaction. But there are some Riemann sums that you do know. So remember, the sum, if it was just like, well, let's do a couple. If it was just the number, say, 1 from k equals 1 to n, then what would it be? Well, I would be saying you do 1 plus 1 plus 1 plus 1 n times. And that comes out to be n. Or if it's the sum of just k from k equals 1 to n, that's saying it's 1 plus 2 plus 3 plus n, going all the way up to n. And we've talked about how this comes out to be n times n plus 1 all over 2. And then the last one that we're going to need here is remember that the sum of k squared from k equals 1 to n, that's 1 squared plus 2 squared plus 3 squared all the way through n squared. That comes out to be n times n plus 1 times 2n plus 1 all over 6. And so these are good ones to know. You should also remember that the sum of k cubed comes out to be n squared times n plus 1 squared divided by 2. So these are the ones you really need to know. And so we're going to try to use these by manipulating this expression. So currently we have the expression, the limit as n goes to infinity of 2 over n times the sum of 1 plus k times 2 over n squared plus 1 from k equals 1 to n. We want to try and manipulate this to make it look like some combination of these guys that we're familiar with. So here we go. First, we can say, okay, well, this sum, this piece squared, is just 1 squared, which is 1, plus 2 times the first one times the second one. So 2k times 2 over n, plus the second term squared, k squared times 4 over n squared, just square that, plus another 1, which makes this one 2. So now we're just summing this up, summing this guy up from k equals 1 to n, 2 over n times that. Okay, let's keep going. Well, we can break up this sum. We can say this is the same thing as the limit as n goes to infinity of 2 over n of one piece at a time. This is like the sum of just 2 from n equals 1, from k equals 1 to n, plus here I have the sum of this stuff. I'll have to leave the k inside, but I can pull out the 2 times 2 over n, so I can pull out the 4 over n. Here I have to leave the k squared, but I can pull out the sum of the 4 over n squared from the sum, leaving this expression. Okay, making progress. Now we use the fact that we know what these are. Remember, we know what the sum of k squared is. We know what the sum of k is. And we know, well, the sum of 1 is 1 plus 1 plus 1 is n. If these were all 2's, this had been a 2 and this had been all 2's, you would have just 2 n's, n copies of 2, or 2 times n. So it's 2n. So that's, this first piece is just going to be 2n, so we still have the limit as n goes off to infinity of 2 over n, plus you have 4 over n, times the sum of k, which we said is n times n plus 1 all over 2, plus 4 over n squared, times the sum of k squareds, which is n times n plus 1 all over 2n plus 1. Yeah, should be a plus 1 there, all over 6. And now, running out of space, now we want to expand these out. So here we go. You get the limit, so it's equal to the limit as n goes to infinity. If you multiply these out, 4, and you have times n divided by n, so just 4, plus, okay, here I have 2 times 4, so that's 8. This is going to be n squared plus n, so when it times out, it's 8n squared plus 8n. All over n times 2 times 2n squared, plus over here you might want to FOIL this really quickly. This is just 2 times n, so it's 2n squared plus 2n plus n plus 3n plus 1, and times that all by an n, and times that all by a 4 and a 2. So it's going to be 8 times 2, so it's going to be 16n cubed, plus 2, 4, 8 times 3, 24n squared, plus 8n, all over 6n cubed times n, 6n cubed. 6n squared times n, 6n cubed. Okay, and now it's like, this is beautiful. Now we can just evaluate the limit. This first piece is just 4 plus. This next piece, again, this is the rule we saw in the first video. You can, since you're going off to infinity, you just have to look at the highest term. So it's just 8 over 2, which is just 4. Plus here you just look at the coefficients of the highest power, 16 over 6, which is 8 over 3. Well, that's the same thing as 8 and 8/3. 8 is 24/3, so this is 32 over 3. Okay, so we just did a whole lot of work to show that the integral, we have this integral here, we just claimed that the integral from 1 to 3 of x squared plus 1 dx comes out to be 32 over 3. That's what we just showed. Now, to check this, we're going to check it with the evaluation theorem. So remember what the evaluation theorem says. The evaluation theorem tells us that the integral from a to b of little f of x dx is big F of b minus big F of a, where big F of x is the antiderivative. So the derivative of big F is little f of x. Big F is the antiderivative of little f. And so let's go ahead and check that this holds true by using the evaluation theorem. According to the evaluation theorem, the integral from 1 to 3 of x squared plus 1 dx, well, first you find the antiderivative. So now you're going to increase the power. Instead of decreasing, you decrease it and take the derivative. You increase it and take the antiderivative. And then you put the opposite, the reciprocal in front. Plus 1 increases up to an x. And we're going to be plugging in the endpoints, 3 and 1. So let's evaluate this. You get 1/3 of 3 cubed, plugging 3 in plus 3, minus plug 1 in, 1/3 of 1 cubed plus 1. And so let's see what we get. We get, okay, 3 cubed divided by 3, so that's just a 3 squared, just a 9, plus 3, that's 12. Oh, getting a little bit concerned. Minus 4/3. Is it going to work out? Well, 12 is the same thing as 36/3 minus 4/3. That gives you 32/3. 32 over 3. And sure enough, that's where we got doing the other method as well. So both ways, we get the same result. So the evaluation method, using the evaluation theorem, this is this fundamental theorem of calculus, and using the Riemann Sum method by adding up more and more rectangles as n goes off to infinity. So calculus works. This is fantastic. Okay, what we're going to do now that we have confidence in the evaluation theorem, is the last page of this review guide simply asks us to work through quite a few integrals. And so let's go ahead and do that. We're going to try and just do lots of examples of integration and see how far we can get. So let's see if I can get through this before my phone runs out of memory. So we're going the integral from -2 to 2. This is a definite integral. It has bounds, so it knows it's going to come out to be some number of 3x to the 4th minus 2x plus 1. So here we go. This just comes out to be, I'll just leave this sheet over here. How do we do this? This is just find the antiderivative. So 4 comes up to 5. Then you divide by that 5. X goes up to x squared. And then you divide by that 2. 1 goes up to x. You put in your endpoints, minus 2 and 2. So it's going to be 3/5 of 2 to the 5th minus 2 squared, because this is just a 1, plus 2, that whole thing, minus 3/5 of 3/5 of minus 2 to the 5th minus 2 squared plus minus 2. Okay. 2 to the 5th is 32. 32 times 3 is 96. So you have 96/5 minus a negative 96/5. So those are going to combine to give you 192/5. Here you have negative 4 minus minus minus. So that's minus another 4. So this guy cancels with this guy. And here you have 2 minus minus plus 2. So plus 4, which is another 25ths. So you end up with 212/5. Onward bound. Let's go to the next one. The next integral asks us to solve what is the antiderivative from 0 to pi of cosine of 5x dx. So there's a couple ways you might think you want to do this. Like, the way I like to tell the story is I say, well, cosine is the derivative of sine. So sine is its antiderivative. So you think that this should be sine of 5x. Except when you take the derivative of sine of 5x, you get cosine of 5x times 5. So like, there needs to be a 5 here before you can do this. But you can't just put that 5 there unless you also put a 1/5 out front. And so you end up with this extra 1/5 term. This whole thing, his antiderivative just becomes your sine of 5x. And then you have the 1/5 lingering, which goes out front. And then you want to calculate from 0 to pi. And so you get 1/5 of sine of 5 pi minus 1/5 sine of 0. And if you remember your unit circle really fast, 5 pi, well, that's an odd number of pi's. That's going to be over here. That's 0. And 0 is also 0. So this just comes out to be 0. It's like, well, how is the area 0? It's like, well, because if you graph this out, you see that it's nice and periodic. Like, it begins at 1 and then goes down and up. And so what happens is the area above and below cancels out. And so you have a negative and positive area canceling with each other. And that's why you got area 0. Okay, let's try this next guy. The next problem is asking us to calculate the definite integral from -1 to 0 of 2x plus 1 to the 5th. And so we're like, how do we do this? And you might say, oh, can't we just increase this to be 2x plus 1 to the 6th and put a 1 over 6 up front? And it's like, yeah, we want to say that's the antiderivative, except the derivative of this would be this with an extra 2 hanging outside. Because when you took the derivative, the chain rule requires a 2. The chain rule would say then times it by the derivative of the inside, and you get an extra 2 outside. But there wasn't a 2 there. So I can't make this jump unless I first put a 2 there. And I can't just put a 2 there unless I also cancel that 2 by putting a 1/2. So I end up with this extra 1/2 lingering in front. And now that's what I'm going to evaluate from -1 to 0. So I get 1 over 12 of, well, you plug your 0 in, it just becomes 1, minus 1 over 12. You plug your -1 in, -2 becomes -2 plus 1 to the 6th, which again is just going to be a copy of 1, which again, so this is just 1 over 12 minus 1 over 12. And so you just get 0. So again, this is 0, and you can graph this out, and you should like look at this and try and figure out what's going on, like why does this have area 0? It's not that it's flat, it's that the area below and above the lines would cancel once again. Okay, let's go on to another one. So this next one from the review guide asks us to find the antiderivative from 0 to 1 of the square root of x plus 1. And it's like, okay, we can do that. And so let's first multiply it out. Because remember, when you have a product, you can't just do the derivative of the first piece, the derivative of the second piece. Why? Or the antiderivative of the first piece and the antiderivative of the second piece. Why? Because derivatives don't work that way. The derivative of a product is some complicated product rule. And so you can't expect the antiderivative to be simple like that. Instead, what you need to do is try and get rid of your product by multiplying it out. So you multiply it out, you get x plus square root of x times square root of x is x. Square root of x times 1 is square root of x dx. Now we can take the antiderivative. X bumps up to x squared. You have a half out front. This is x to the 1/2, so it becomes x to the 3/2. You increase a half by 1, and then you put the reciprocal in front, 2/3. And we're going to evaluate that from 0 to 1. So this comes out to be a 1. You plug 1 in. It becomes a half plus 2/3. Minus, plug 0 in. Well, that's all just 0. So you just have a half plus 2/3. This is just 3 over 6 plus 4 over 6. This is just 7 over 6. 7 over 6. Okay, one more problem with the evaluation method. What is the antiderivative from 0 to 1 of e to the 2x dx? And so this is what I like to say. You say he should just be, you might think he's just e to the 2x. But if he was e to the 2x, then his derivative would be e to the 2x times 2. And it's like, so you need there to be a 2 there before you can do this antiderivative. But there's not a 2 there. Well, you can put a 2 there if you also put a half out front. So you need a half out front. So 0 to 1. And you get 1/2 e to the 2x. So that's 2. Minus 1/2 e to the 2 times 0. So that's 0. So that's just a half of e squared over 2, minus e to the 0 is 1, so it's e over 2 minus 1 over 2, or e squared minus 1 all over 2. So that's it for evaluation theorem, although there's still a number more integrals that we can solve. So here we just have some indefinite integrals. So then we're given on the review guide these indefinite integrals, like the antiderivative of 1 over the square root of 1 minus x squared dx. And the key thing is, since you don't have bounds, this is going to come out to be not a number but a function. Actually it's a family of functions, because you're going to have this plus c. So the plus c things mean you expect it to be a family of functions. And what is it? You just have to remember, this is the derivative of what? And if you happen to study this, you remember that's the derivative of arcsine of x plus c. Or you can call it sine inverse. Same thing. Sine inverse of x plus c. Okay, the next one is the antiderivative of x squared over x cubed plus 5 dx. And this one, maybe you can't just see it immediately, so maybe here we should do this You Substitution. Right, to make things a little bit clearer, let's make one of these pieces U. And typically you want to make the most complicated piece U. It's like or you're looking for a function inside a function. Like, okay, well, we have the division by this other function. So it's like, that's probably your u, is x cubed plus 5. And already you're thinking, I know I'm going to take the derivative of u, so I'm hoping that I have like something like the derivative of this, and yeah, x squared is close to the derivative of x cubed, so I think I'm on the right track. Right? Okay, well, let's go ahead and check. The derivative of x cubed is 3x squared. The derivative of 5, since it's by itself, it vanishes, and then this is dx. And you're like, oh, this is pretty good. I have an x squared dx, so that's this part, but I need a 3x squared dx. So there's two ways to think of it. You can put a 3 there and then put a 1/3 out front, but if that's confusing, you can also just think, well, I can move that 3 over to the other side, and then I'm saying I'm replacing my x squared dx with a 1/3 and with a du. And then this whole thing becomes the integral of my x squared's gone, I've already dealt with it, so I just have a 1 on top of the fraction, and here I have x cubed plus 5 is just u. So I end up with the antiderivative of 1 over u. And we know that is ln of u. So I have 1 over 3 ln of u plus c, which comes out to be 1 over 3 ln of my u, which is x cubed plus 5. X cubed plus 5. You might want to put absolute values just to indicate that this has to be a positive. You can't take ln of a negative number. Okay, let's do the next one. What is the antiderivative of x times the square root of 1 minus x? And here you probably really do need the u. It's pretty tough without it. You're like, okay, notice I have this function inside the other function. So when taking the derivative, when going this way, we're using the chain rule. So we're now trying to undo it. We undo the chain rule with u substitution. So we say let u be that inside function, 1 minus x. And so now you're like, okay, well, this is going to become the antiderivative. This piece here is going to be the square root of u. But what happens to x? What happens to this x? It's like your du is going to be, let's think, well, it's a negative dx. It's like, that doesn't really help. I still have this x lingering. But notice if u is 1 minus x, then you can move your x over, you can move your u over. You get x is 1 minus u. So this right here is just 1 minus u. And dx, if du is minus dx, then dx is minus du. So you have a du and you have a minus. Du and minus. So then this thing comes out to be negative the antiderivative. Like, how does this help? It's still a mess. But now we can distribute. Here we can't distribute. Can't distribute within the square root. I mean, you still have the square root, there would be a mess. But here you can distribute. This is just going to be 1 times u, so that's just a copy of u to the half, minus u times the square root of u, so that's u to the 3 halves, because u is u to the 1. And so now it's something that we know how to solve. It's like, okay, we can do this. This just comes out to be equal to negative, bump up u to the half, u to the 3 halves, 2/3 u to the 3 halves, minus bump up 3 halves, so u to the 5 halves, 2/5 u to the 5 halves. I will just go ahead and distribute my negative. So this is going to be negative 2/3. What is my u? Well, u is 1 minus x. So 1 minus x to the 3 halves. Negative, negative, plus 2/5. What is u? U is 1 minus x. 1 minus x to the 5 halves. Plus c. Just forgot my plus c. There we go. We started out with a question about x's. I changed it into u's to make it easier to solve, but in the end I changed it back into x's. You know, if someone asks you a question in the language of x's, You answer in the language of x's. U was just a tool we used to help us along the way. A couple more here. What is the antiderivative of x sine of x squared? Notice, like, here you have a function inside a function, and something looking like its derivative is outside. So this is prime. This is classic U substitution example. It's like, look, right there, you have a function inside a function. You have an x squared, and its derivative would be 2x. So it's like, great. I just need there to be this 2x. Okay, I almost have 2x. I have an x. I don't have the 2. So you could think, well, to move the 2 over, that's a half du. So that's telling me, okay, I almost have what I want, except this x dx, the x and the dx get replaced with a half du, and the sine of x squared gets replaced with sine of u. Or another way to think about it is, you know, I really need there to be a 2 in front of this x before I can change this 2x dx into du. But I can only put a 2 there if I put a half there. And that's why I end up with a half right here. Either story explains why there's a half. And then you're like, great, sine is the derivative of negative cosine. So his antiderivative is negative cosine. So you have negative 1/2 cosine u plus c. But they asked us a question about x's, so we should answer in the x language. So we end up with negative 1/2 cosine of x squared. That's where your u is, plus c. Okay, last one in this little section. We're trying to find the antiderivative of 1 over x ln x dx. And so maybe it's not obvious, you know, what is your u and what is your, you know, is u x? Is it, well, ln x maybe? Is it x ln x? Maybe it's not obvious. Let me rewrite this. It might help a little bit. 1 over x, 1 over x times 1 over ln of x dx. And maybe this helps a little bit because you're like, notice here I have this like ln of x, and the derivative of ln of x is 1 over x. And so that's really promising. You know, if you make your u ln of x, then the derivative of u, your du dx, is 1 over x. So your du is 1 over x dx. And you're like, that's pretty promising because you have 1 over x dx. That all becomes just du. And now I have 1 over ln of x. So 1 over ln of x becomes 1 over u. Then, when I take the antiderivative of 1 over u, it's like, oh, that's ln of u. And so you end up with, plus e, ln of u, but u is ln of x. So you end up with ln of x plus c, which is pretty crazy. But that's what we have. It's like we have some Starry Night going on here or something, making something pretty crazy. Okay. What we have now in this next section of the review guide is it asks us to go through and evaluate a number of these integrals. But it's the derivative integral. And so you might be trying to remember like a derivative of an integral. Like what is going on there? So let me just, I'm trying to articulate the principle and then we'll see it in action. So if you have the derivative of the integral from like, I don't know, 1 or whatever, 2 or 3 or whatever, to x of, say, some function of t, dt, remember, it's like evaluation theorem. What is this going to be? Well, here it's just, this is going to be the antiderivative of f, evaluated at x, minus the antiderivative of f, evaluated at 1. But then I'm taking the derivative of that. And so it's like the derivative of the antiderivative of f is just little f of x. Back to what it was originally. And then the antiderivative of f of 1, it's like, well, what is f of 1? Well, it's just 1 plugged into a function. It's going to pop out a number. So this is a constant. So when I take the derivative, this piece is gone. So I just end up with just f of x. Little f of x. So when I have a problem like, what is the derivative of the integral from 1 to x, or from 3 to x, or whatever, of e to the t squared minus t dt, this fundamental theorem of calculus right here tells you, look, the derivative is just, I'm doing the antiderivative. They're just canceling. The integral is just the antiderivative. So these just cancel, giving you just the original function, this e to the t squared minus t, both x's plugged in. So e to the x squared minus x. These guys cancel, but the x's take the place of the t's. So, pretty straightforward. How about, though, if I had instead the derivative of some integral from whatever value, this next one's doing it -2, but whatever value, to some other function like x cubed. Well, in general, for any function, any f of t, it's like, it's going to be the same argument. It's going to be the derivative of the antiderivative of x cubed minus the antiderivative of -2. And so it's going to come out to be, I'm sorry, this should be dx. The derivative of the antiderivative is little f of x cubed. But then, this chain rule kicks in. Chain rule says take the derivative of the outside, big F becomes little f, keep the inside the same, x cubed stays x cubed, but then times it by the derivative of the inside. So times it by 3x squared. And then this other piece, it's like, what's going to go on here? Well, this is just a constant again. F of some number is a constant, so its derivative is just 0. So you don't have to worry about it. So for our particular problem, where we have the derivative of the integral from -2 to x cubed of the square root of 1 minus t dt, you say, okay, well, first, these are going to cancel, so just plugging in the top guy is just plugging in the x cubed for the t, but then it's timesing it by 3x squared. And then the bottom, well, when you plug it in, you get a constant, so you're going to take the derivative at 0. So it's just this. That's all it is. Last one is very, very similar. We want to know what is the antiderivative, or what is the derivative of the integral of sine of x to cosine of x of 2t dt. And so you should think like, I'm going to take the antiderivative, I'm going to plug in cosine, I'm going to take the derivative, so it's just the original function with cosine plugged in, but then times by my chain rule the derivative of your cosine, which is minus sine of x. Minus the antiderivative with sine plugged in, but then you take the derivative, so it's just the original function with sine plugged in, but then by your chain rule, times the derivative of sine. So that's times cosine of x. And these are actually the same thing, -2 cosine sine, -2 cosine sine. So this just comes out to be -4 sine of x cosine x. Okay, very last problem. It has a few examples where they want us to say, hey, we're going to give you some information. We're going to say that the antiderivative from -1 to 4, 4 times the derivative of a function is 12, and from -1 to 0, of 2 times its derivative is 6. Figure out what it is from 0 to 4 of f prime. And so it's like, okay, let's see what we can say here. So I have the antiderivative of -1 to 4 of 4 times f prime of x is 12. I have that 0, -1 to 0 of 2 times f prime of x is 6. So like here, I can pull this 4 out and then divide by it. So that would tell me if I'm just going from -1 to 4 of f prime of x, it should be 4. No, divide by my 4. So it should be 3. 12 divided by my 4 gives me 3. And then this one tells me that if I go from -1 to 0 of f prime, well, divide by this 2, I can pull the 2 out and divide by it. That's 3 as well. Okay. Now I want to know what is the area from 0 to 4. And maybe like a little picture will help, because it's like I want to know, okay, so I know the area, I have some area from -1 to 0. So from like -1 to 0, I know this area is 3. I know that area is 3. And I know the area from -1, so it's like this area is 3. But I also know that the area from -1 all the way to 4 is 3. So from -1 all the way to 4, that also comes out to be 3. So now I'm trying to figure out what is just this area right here. And so the pictures suggest this perhaps. I mean, it's a little bit misleading the way I drew it. But the key insight is like, well, whatever the area from 0 to 3 is, it should be the case when I add that area from -1 to 0, and not 0 to 3, 0 to 4, whatever the area from 0 to 4 is, when I add that to the area from -1 to 0, I should get the area from -1 to 4. Right? Because that's the area from -1 to 0, plus the area from 0 to 4 is the area from -1 to 4. Okay, so let's go ahead and see what we can say. Well, we just said that this area from -1 to 0 is 3. We said this area from -1 to 4 is 3. So that means this area must be 0. So that integral is 0. Very last problem. Let me grab a piece of paper. Okay, so here we go. Very last problem. I'm told 2 pieces of information. F of 2 is 3, and the area of 3 f prime of x dx is 6. The area is from 0 to 2. So the definite integral from 0 to 2 of 3f prime of x dx is 6. Well, here we do something similar to the top. I pull my 3 out, I divide by it, so I get that the area under the curve from 0 to 2 of f prime of x dx is divided by 3, so now that's 2. And then I go, okay, well, according to my evaluation method, my evaluation theorem, this thing is just the antiderivative, so that's just f at 2 minus f at 0. So I have that f of 2 minus f of 0 is 2. Is 2. But I was also told that f of 2 is 3. So I have that 3 minus f of 0 is 2. Hence I conclude f of 0 must be 1. Okay, victory. Yay, done. Fantastic. So hopefully that'll help you review some of the major problems. For the exam, more can be fair game, but that should give you an idea of some of the major types of problems that we've seen so far in this course.